hopefully each one of you has gone through the problem of trying to solve it, or at least have read the question. So I'll just share my screen. Hopefully my screen is visible. Can someone please confirm if my screen is visible? Okay, perfect. Thanks. Right. So this is the question that have been given in points in a d-dimensional space. I'll just read the question. So you have been given in points and in a d-dimensional, and every points are not connected initially. So the points in some sense are not being connected by any means. They're all their own component in the space, and the points are not guaranteed to be distinct. So you may have a situation where in some space you have 2 points that are overlapping with each other. So then in some sense you can say that if you have a set, then some points will be on the same coordinate. These points are on the same coordinate. This is a different point. And so this is just the definition of how you calculate Euclidean distance for a d-dimensional space. And your initial score is 1. Okay. And then what the rule of the game is follows. For any 2 points in the space, you have free to connect them. And once you connect them, your score gets multiplied the distance between them. So for instance, your score is, and then you have these 2 points. And if you connect them, then the distance is d. Then your score is basically 1 into d. And then you connect d1. So score multiplies by d1. And you can connect them as long as the new connection does not form a cycle. Then the first cycle, once you have these points, you cannot connect them in this manner or in this manner or in this manner, because you will get some cycle, right? So you cannot connect that in this manner. And the basically the definition of a cycle, you can say that in a precisely mathematical or in a network sense of language, you can say a cycle is formed and there are at least two distinct points, distinct paths from for two vertices. If I have a vertex A and a vertex B, and if I have two paths from which I can go from A to B or from B to A, then I go cycle to the graph. One network. Okay. And every time you connect a pair of vertices, your score is multiplied by the square of distance between them. So the distance would be your score is basically into A, then some one B2. Right? And this is just specification of the coding problem. Whether you use any pocket potato, this number has to get smaller. So that that's what cost an over. Right? Uh, so if you have any doubts regarding the problem statement, just let me know in the chat right now. I'll just wait for a minute for a stop and just the problem statement is clear. That would be great. or anyone wants to share their thoughts for the problem? Hopefully, the problem statement is clear. So let's go ahead. So I'll just make sure that you all understand what is meant by distance and dimension space. So we are used to seeing distance in pure 3D. If we have points x and y, consider the coordinates of x and x1 to x3 3D. I'm talking about 3D, right? And the coordinates of y, y1, y2, y3. Then what we do is we just square root the distance between x, x and y.
So your voice is
X1.
not clear.
My voice is not clear. Okay, can anyone confirm if my voice is breaking for all of you, or
Yes, it's breaking for me also.
okay. Is it still breaking? Oh, is it still breaking, or is it fine?
It's fine for me.
Fine, I think.
Okay, fine. Okay, thanks. Right. So I was talking about the distance in 3D. What you do is basically pairwise subtraction of all the coordinates, and then you square them, and then you sum them. Right. So basically, for 2 points in d-dimension space, you can write the distance of these. This is in mathematical notation, square root of sum of uh, fraction of pairwise coordinates, and the sum of squares of subtraction of pairwise coordinates whole root over. So this is in 3D because you have I from I to 1, 3. So in RD, that is the D dimension, they're points in D dimension, so their coordinates will be x1, x2, x3, and y1, and y2. Right. So this will be something like square root of summation xi minus yi whole square is equal to 1 to d. Right. Hopefully this is clear. I think now we can build up some of the logistics of the problem, or of how I actually going to model it. So this problem is basically a lattice point in a d-dimensional space, and for d-dimensional space, this information is used to calculate the distances between the points. Right. So just by looking at it, I think this is clearly a graph problem, because you are trying to connect different vertices that are in the space. So you are trying to connect vertices that are in the space, and they will in turn form a graph, right? So it's clear that why this is a graph problem. Now we we want to maximize our score, right? So our initial score is 1, and then you want to maximize the score. Okay. So consider a graph something like this. And then what do you think? Because you want to maximize the score, what do you think will be the weight of the edges? or would it be weightless? Every vertex is basically a point in space, right? So this is a point in space, point in space, point in space. And because we are saying that we want to model it as a graph problem, there would be an edge between them. So what do you think will be the weight of the edges? Anyone wants to answer? I'm saying that this is a graphical problem, and once you so once you connect 2 points, your score gets multiplied by the distance between them. So what do you think should be the weight of the edge connecting 2 points? Yeah, hi Christian. I think I can brief the problem once. This is basically we're discussing week 7, and this is the programming assignment for week 7. And basically, this is saying there are n lattice points in a D dimension, including this is the formula or section L2 norm, known as L2 norm in D dimension. Right. So I'm saying that if I want to model this problem as a graphical network, and I'm saying that these vertices are basically points in space, right? These are the points in three-dimensional space. Then what do you think should be? And once I connect two vertices by an edge, my score gets multiplied by the distance, square root distance between them. So what do you think should be the weight of this edge? Or should it be weightless? Like all the weights should be one. What do you think? I'm audible?
Hi, is my voice clear now?
Yeah, better.
Right. So I was basically discussing about I was saying that what should be the weight of this edge. if I'm saying that I want to multiply my score by the square of distances, once I connect these edges, sorry, these vertices, so what should be the weight of the edge? I mean, you can take a guess.
The distance between them.
Yeah, precisely. Because your n is going to multiply the score by the distance. So just might as well take the distance as the weight of the edges. Right. So I think we have built the intuition of how this will be a graphical network and how you can model this in terms of vertices and the edges. Now the follow-up question is like, what kind of graph will this be? Will this be a complete graph? Will this be a bipartite graph?
Complete.
Right. And why do you say so?
Because every pair of nodes are connected.
Yeah, precisely. So thank you so much for answering. And this is because once you have the chance to connect every possible, you can, there is a rule that you can play as much as you want until you cannot do any move, right?
Yes.
So in the starting, what we can do is we can just connect all of the possible vertices that we can connect, and in turn this will be a directed edge, because sorry, undirected graph, because the distance of the weight of the edge from u to v will be the same as the weight of the edge from v to u, and there is no point in using excess space in storing this as a directed graph. So I might as well just turn this in an undirected graph, because we are talking about distances as weights, right? And since we are talking about distances, this will be every distance or di, that is the weight of edge, will be always greater than or equal to 0. Okay, I think this is fine. And then so we have built this graphical network. uh, I mean, this is a complete graph. I might miss some edges, but every vertex should have a degree of 4. I think I just repeated 1, 2, 3. Yeah, something like that. I mean, you get the idea, right? So every vertex should have a degree 4, and it should be connected. There should be only one edge between any pair of vertices. So this edge should not be there. I might as well just redraw it. Okay, fine. This is fine. And so this is D1, this is D2, this is D3, D4, D5, D6, right? So there are 6 edges, so 6 distances, and this is point 1, 2, 3, 4. Now I basically have to, my initial score is 1, and for this problem, let D1, D2, D3, D4, D5, D6 be distinct, right? Something there is no vertex that coincides with the other vertices. So I will have only unique distances in my graph. And now you want to maximize the score, right? And by my assumption, I am taking as if di is greater than dj, then I is greater than j. Or d6 is greater than d5 is greater than d4 greater than d1, right? So can anyone tell me what is the first edge that I should take so that I can get the maximum score?
D6.
Okay, perfect. So d6, then
D5.
okay, then
But then D4 will form a cycle, and we don't want that. So D3.
d2,
D3.
d3, okay, d3, right? Then
We are done.
right, then done. So can you just tell me the final score? That would be great.
D3 plus D5 plus D6.
No, the score gets multiplied by every
Oh,
edge.
okay. Yeah, D3 multiplied by D5 multiplied by D6.
So note that at this point we're not um, storing the we're not storing the distance between vertices as edge weights. We are storing the square of the distances, because okay, if this is the distance, then your score should get multiplied with the square of the distances. So I'm just letting this to be the square of distance between the vertices. I hope this is clear, right?
Yes.
Okay, right. Or I might as well, if this is the distance, then this is d squared. Okay. Right. So basically you did this, but what if I told you that, you know, um, these are distinct, but in other case, we have a network, something like the same network, but now edge weights are allowed to be zero. You can have zero edge weights. Okay, just 1 second before moving to this case. So basically, if you can see, we are looking for a tree in the graph, right? You're looking for a I hope all of you have heard about minimum spanning tree, but for this problem, you're trying to find a maximum spanning tree. And can you name any two algorithms, or at least one algorithm, that you use to find minimum spanning tree?
Prims and Kruskals.
Precisely. And the nature of these algorithms, are these dynamic, greedy, or like optimum algorithms?
Uh, these are optimal, I guess, for minimum
Yeah,
spanning
these are
tree.
in turn, I mean, these are optimal for cases, but they are greedy in the sense
Yeah.
that at every step, you're trying to take what's the local best choice you can do, right?
Yes. Yes. Yes.
Right. So in minimum spanning tree, you basically start with the edge with the lowest weight. But
Yeah.
here, I'm saying that we just start with an edge with the highest weight. And in MST, you're trying to maximize the weight function, that is the summation of WI. But here, you are trying to maximize the product of WI, right?
Yeah.
So this is the maximum spanning tree. But I'll refrain from even using the word spanning, because as you will see in some of the cases, you cannot include all of the vertices in a maximum spanning tree. The tree has to span all the vertices. That the set of vertices in your resultant tree should be the set of vertices that are present in the graph. But in this question, or in this some of the cases in this problem, we might not able to retrieve the whole vertices, the set of vertices as an answer. So let's see that case. Um, so is this clear that why are we going for? So basically, you can run Prims or Kruskal or on even this question, and for if you are running Prim, for example, or Kruskal, for example, in Kruskal, what you used to do is first take the minimum weighted edge, then they take the second minimum weighted edge, then the third minimum, and then try to connect these and do not form a cycle. If you form a cycle, then reject that edge. And in this case, for running Kruskal, you take the maximum weighted edge, then the second maximum, then third, fourth, and so on, till you do not get a cycle and you have the complete set of vertices. Right. So is this clear why we are trying to use Kruskal or Prim? That is why are we trying to form a tree? Because we do not want a cycle. That is the motivation for finding a tree in the graph. A spanning tree, but that might not span all the vertices. If there is any question or any doubt or anything you want me to repeat, I can repeat. Okay, I hope this is fine for now. So let's take a case where the network is something. I'm still taking 4 vertices. Okay. But this is the edge weight 0. This is the edge weight, I'll say 1. This is the edge weight 2. And this is the edge weight 3. This is the edge weight 4. This is the edge weight 5, or something like that. Okay. So do you think this is the correct graph? I mean, is this situation even possible?
No,
Why? Why?
because the top two nodes are at the same position,
Yeah, because
but the distance from them to other nodes aren't equal.
right. I think you captured it perfectly. That was I trying to motivate. So the thing is, this graph should have been something like, so in reality, these 2 points coincide, right? So if you're trying to model this as a graph, this will something look like, if this distance is 4 and then this distance should also be 4 and this distance is 2, then this distance should also be 2. So is this right now?
Yep.
Yeah, okay, thanks. Right. So um, coming back to the problem, so we are trying to find the MST. So first we'll take any edge. So if we take this edge, then we take something like this edge, then we take a, so we cannot take this edge because this will cause a cycle. So we'll take this edge, and then um, I'll- 0. And then you cannot take this edge because this will form a cycle. So you will take this edge. So is this the right, like, so what will be my final score in this case?
0, but it's less than 1, which we initially had.
It's less than 1. Yeah, it's less than my initial score. So I might as well have not done anything, right? I would have gotten a better score.
Yep.
So this happens because, so notice that I should not be including this edge, right? I should not be including this edge in my final tree. So what I should be doing is I should just have, yeah, I should just keep it like this. So my final score would be 4 square, 3 square, and 2 square, right? So this is not 0. This is greater than 0. In fact, greater than 1. So I'm doing something right. So this is not an maximum spanning tree in a sense that it does not span all the vertices.
Yeah.
Yeah. Okay. Yeah. But the thing is, you are going to maximize the weight of the edges you take in a tree. So that's why you can run greedy algorithms. And in fact, there is a very nice quote on this, that greedy algorithms like Prim and Kruskal that tend to maximize or minimize functions like weights. So they, for so the quote is something like, Kruskal and Prim's algorithm can maximize or minimize monotone functions over weights. So this F can be sum or even product. So in a sense that it is saying that if you run Prim's or Kruskal algorithm and you're trying to minimize the sum of weights, it will give you the same result as trying to minimize the product of weights if the weights are non-negative. And that's why we are trying to use Prim and Kruskal, because we used to use Prim and Kruskal when we wanted to find this minimum or maximum sum of weights. But here we're trying to minimize or maximize the product of weights. In fact, maximize the product of weights. Right. So this is just a subtle point I am wanted to make, because I think this is relevant in for
But
algorithm.
but only if the edge weight isn't less than or equal to 1, less than 1.
Less than 1. No, this will.
Because if the weight is less than 1,
Is less
then
than or equal to 1. Yeah, non-negative and less than equal to 1. You're right. Because multiplying that will decrease,
yes.
but adding that will increase. Yeah, right. Okay. And yeah, thanks for the remark. So right, so we have established that we are trying to calculate an VST, sorry, MST, and we are going to use Prim's or Kruskal. Now we want to decide between Prim or Kruskal, and then we say that we, in Prim's algorithm, you start with the maximum weighted edge, and then you maximum weighted edge for if you want a maximum spanning tree. So this is W1, and W1 is greater than W2 up to Wn, and n is the number of m is the number of edges in a graph. And then you try to build the tree further. While in Kruskal's algorithm, you have a graph. First, you take the largest edge. Just going to extend this further. Then you take the second largest edge, then the third largest, then the fourth largest, till it does not form a circle, right? So these two vary in the sense that how do you connect the vertices. So this has a time complexity of order of, I think, v square, and this is the time complexity of order of e log e, because you have to first take the weights of all the edges and then sort them, and there are e edges, so sorting them in using merge sort, quick sort, or any optimized sorting algorithm will take n log n, that is e log e. And I think one of you mentioned that it will be a complete graph, right? So what are the number of edges in a complete graph if the set of vertices, if the cardinality of the set of vertices is v? So if I have v vertices, what is e for complete graph?
V into V minus 1 by 2.
Right. So that is v combination to like you by using combinatorics, but yeah, that's fine. So this is in turn v square. So order of e log e is order of v square log v, and Prim's is order of v square. So I think this Prim algorithm would be slightly better than using Kruskal's algorithm for this case, but yeah, that's just for the logistics of coding. And then, so just tell me for this case, I just have one subtle doubt. So if I have a graph, something like this, 0, 0, 0, 0, 0, 0, 90. So if I run Prim on this graph, first I'll get this edge, and then all the neighboring edges are weighted 0, so I'll just stop, right? Because if I try to build this tree further, I'll have to take at least one of these neighboring edges, but that will give me the product 0, so I'll just stop. But if I do the same for Kruskal's algorithm, if I try to do the same for Kruskal algorithm, I'll just take this edge and then this edge, and I cannot connect them further because I'll get a score 0. So here my score is 100 into 90. Here my score is 100. So I just mentioned that you should use Prim's algorithm, but Prim's algorithm seems to fail in some situations. So what is wrong with this case? Is the question clear?
Yep. Wrong with the graph?
I mean, why I'm getting a score of 100 with Prim, but a score of 9,000 with Kruskal? Or this is 100 square, this is 102.
I think because of the fact that we are multiplying the score. If it would be the sum, then I guess it would give the right answer.
Right, but for the question, why? I mean, these two should work in principle, but these are not working. So why are these not working? I mean, if you can, I think you have answered this question before when I asked the same question. I mean, this was similar to what I mentioned here. So the answer is this case will never arise in our question.
Oh yeah.
right? Because these are weighted 0, so these points coincide, these points coincide. So if this is has weight 100, then this should be 100. This cannot be 90. uh, is that right?
Yes.
Yeah, so this is 100 and this is 100. I think that is right. Hmm. So I think so the whole algorithm basically boils down to, if I'm using Prims, so that is calculate the maximum spanning tree, and then you stop as soon as the next uh, edge to be added is 0. I mean, if all the possible edges that you can add, the best is 0, then you just stop. You do not build your tree further. And just for the the code logistic, so for example, if you have till now you have built a tree T, and your score is ht, then if you add an edge, add edge with distance di, then you multiply your score by st into di modulo the value that is given. You don't take the mod at end, because it might be the case before even reaching the end you just get an overflow. So just to prevent overflow, just take mod at every iteration. Okay. I think we are done for this, and I think this should be easy to code, because this is just an Prim or Kruskal algorithm, and you just have to take the maximum spanning tree. That does not necessarily span the whole graph.
But I got TLE with Kruskal's algorithm. And you
Sorry?
also mentioned I got TLE with Kruskal's algorithm.
You are getting?
TLE.
Yeah, you
Time.
will really in Kruskal algorithm, because Kruskal algorithm is slower. In fact, I mean, Kruskal algorithm is order of uh, v square log v, and this is Kruskal algorithm, and Prim's algorithm is order of v square, right? So the test cases have been v something like 666, I believe.
Yeah.
So the test cases are something that this will fail and this will pass because of this log v
Okay.
factor. So
But
I
even in Prim's algorithm, we put all the edges in a priority queue, right? So at the end, we'll almost have E edges in the priority queue.
no, yeah, right. So the thing is, in Kruskal algorithm, you okay? Let's just talk about the whole question, right? So
Yeah.
firstly, you calculate all the distances, and if you have v vertices,
Mhm.
and you calculate distance for all pairs, how many calculations are you be doing?
Almost
Approximately
V square. Yeah.
almost v square, right? That would be in fact v into v minus 1 by 2,
Yeah.
right? And then for Kruskal, you have to sort these distances, because you're always going to take the maximum weighted edge,
Yeah. Yeah.
right? So sorting will take v square log v, and then you take and then just you do some visited marked or things, and just build up the tree, and that would be less than v square. So the whole that would be in fact v square, because you're going to try every edge. So
Yeah.
that's something like a square log v plus v square, and that is in fact v square log v.
Yeah.
But for this is v square log, but taking this order is same as 2v log v, so this is order of v log
Yeah.
v. And but for Prims, what you do is you do not need to calculate like even if you calculate all the distances, that is order of v square, and then this is just for calculating distances. calculating distances, and then you just run the Prim's algorithm in a priority queue or in priority queue. And priority queue is maintained and it does not require sorting. So there is not any v square log v. And then you do DSU, and DSU is still less than v square log v. That is not the bottleneck of the complexity. So this is still any factor, and f of v will be always less than v square. So this is in turn order of v square. This is,
Okay, I get it.
yeah, so Prim should get accepted. Kruskal might, yeah, the test cases are such that Kruskal will fail.
Yeah, I was more comfortable with Kruskal, so I didn't even try Prims. I thought
Yeah,
it's the same complexity.
right. I think Kruskal is indeed something most of us would be comfortable with, because you're anyways going to, it's a very intuitively greedy approach, because you're going to try maximum, then next maximum. Prim is something like you're just going to build the tree. So, and it requires a mathematical proof as to how would it be something that Kruskal can do and Prim can do the same thing. So that is this. Hopefully this is clear, and I'm open to any questions you have for this assignment. But yeah, that would be it for week 7.
Yeah, thanks a lot, Nipun. I think let's just wait for a couple of minutes to see if there are any more questions or comments. And yeah, in the meantime, I'll say that, yeah, for most of these techniques that we learn, so for instance, even for shortest paths, we see that there are many different approaches and algorithms. Even to begin with, we started off graphs with BFS and DFS. And most problems that can be solved with BFS can also be done with DFS and the other way around. I mean, this is, of course, not always the case, but often the approaches are interchangeable. So usually we have like a sense of comfort with one of them, and we say that, okay, that will be our go-to algorithm if we have a problem where we see that a particular traversal, if it can work, then I mean, if both of them work, then we will kind of implement our preferred one. And whenever you have the luxury of doing that, that's great. But often you might be in a situation where you really need a modification or an adaptation, or even between BFS and DFS, one of them would be much more natural to implement. The other one may be a pain to modify, or may not be suitable at all. So in general, while I think we'll all have our soft corners for being comfortable with a particular approach or whatever, it's probably a good idea to prepare yourself with practice and in multiple approaches, because that way you have a more robust toolkit, especially when you're actually in a contest. Sometimes even if ये थोड़ा तुक्काबाजी type advice है, but sometimes especially when you are running out of time in a contest, you might just throw a different approach at it and see if that works, and then when you're up solving, you can go back and try and analyze. So this problem was, I think, specifically set up so that Kruskal would end up with a TLE, but Prim's would work. So so again, if you are in a similar situation in a contest, even though you may not have the time to think through why a particular approach may end up actually doing better for a particular situation, if you're comfortable coding it up, it's like something that you can quickly throw at it just to eliminate the possibility that ye to nahi hai. Matlab, if you're comfortable with both, then you have the advantage that you can at least quickly try the other approach. This will be true for also, yeah, like I said, shortest paths, for instance, flows. For flows, I think Dinnick's algorithm is probably the most commonly used one anyways. But for other problems, they actually, so in fact, if you look at the competitive programming textbook, which is there in the references, they actually, for most of these things, they kind of tabulate hints for, like look at the limits, look at the kind of graph that you are working with. And if it's such and such a situation, then perhaps this version or this algorithm would be the most, well suited for this kind of a scenario. So I think Kruskal is definitely a good start. And I hope that by the next time that we're doing this course, we'll kind of figure out how to do maybe some sort of partial grading or subtasks like CodeChef has, so that at least we're able to get some partial credit for, being on the right track and, using an approach that was very close to the intended one. So I'm sorry that we're not able to do that in this version, but
one test case got passed
okay,
out
all
of
right.
5.
Yeah, I don't know. I don't know if you end up getting like partial credit for that. If you do, then that's good. But yeah, I'm not 100% sure how exactly. I think yeah, actually, I think we do give. I mean, when we upload the test cases, we do have to give certain weights. I assume those are for the scores. So if you've gotten some partial credit, then that's good. But I guess we should probably do it as more explicit subtasks, saying that, well, for these test cases, you're promised that the limits will be such and such, so that you can kind of plan accordingly. Right now, it's a bit kind of ad hoc. But in any case, yeah, I hope that at least it's clear now why we have a differentiator here between the two approaches, and hopefully you had fun thinking about the problem. I guess. Yeah, I mean, for me, an interesting follow-up question was to also think about maybe the number of distinct spanning trees, and also I was also wondering if, yeah, I mean, if you just pretend that there are no duplicates and calculate one minimum spanning tree, is there some formulaic way in which we can use that quantity and then derive? So for instance, if every point is duplicated a uniform number of times, my guess is that you can just take the cost of the minimum or the maximum spanning tree, the maximum spanning tree in this case, and probably just multiply it by the number of times that a point is repeated. But in case it's not uniform, maybe there is no combinatorial formula like this. But these are kind of like maybe interesting follow-up questions to sort of think about. Also, I guess I wanted to say, I don't know if, yeah, I don't know if people are keeping up with the ad coder contests, but I think the recent ad coder contests have had a lot of nice graph problems. So I think I've spotted at least one BFS TFS problem, a couple of max flow problems. In fact, one of them was very close to the max flow problems that were discussed in the lectures for this course. And there've been a couple of shortest path variations. So even if you have not participated in the contests live, I would recommend checking out the recent ad coder contests for some fun graph problems that seem to be pretty close to the kinds of things that we have been discussing in the course material. Also, a small announcement regarding the assignments. I think for logistical reasons, we ended up sort of clubbing the week 8 and week 9 assignments because they're both related to flows. So we'll have some sort of a common deadline for both of them, and they should be, I think you already have an announcement, or there will be an announcement very shortly for both of these assignments combined. So I wanted to also mention that. And I think next week, because we will still be like the flow-based assignments will still be under discussion. I think what we will end up doing next week in the live session is to maybe just have a sort of a general doubt clearing session, across all weeks, and or we will just pick up some fun problems from recent contests that hopefully are from topics that have been already covered in the course, and try to solve them online. So we'll do, these are the things that we'll do next time. We won't be doing, and then I think the week after that, we will do both of the coding assignments together in one live session. All right, so on that note, I think, yeah, we're close to being on top of the hour. So if there are any questions, let me just quickly check the live stream if there's anything there. Okay, there seem to be a few questions. I'm not sure if those of you who asked them are still tuned in, but I'll try to quickly take them. What is the difference between randomized and probabilistic algorithms? Well, in general, I think the phrase randomized algorithms are typically used to refer to algorithms which make use of randomization within the algorithm itself. For example, if you assume that you have access to some sort of a generator of random bits, and you kind of use that generator to flip some random bits and use the outcomes of those flips to make some decisions in your algorithm. So you may have seen things like randomized quicksort, where you sort of hypothetically might be rolling a n-sided die, a fair n-sided die, to figure out what pivot you should choose for the next round. Well, I mean, by n, I just mean the length of the current array that you're working with. So that would be randomized algorithms. Probabilistic algorithms, and I mean, I'm not sure exactly what context you saw that in, but typically we talk about probabilistic analysis to talk about the fact that the inputs are coming from a certain probabilistic distribution, you take a normal deterministic algorithm and often try to analyze it, analyze the performance under the assumption that the inputs are being sampled from some distribution. So it's usually a probabilistic analysis that you're doing. So that's the distinction. In randomized algorithms, the randomness is functionality of the algorithm itself, whereas in probabilistic analysis, the stochasticity or the randomness is in the manner in which the inputs are being drawn. So at a very high level, that is the kind of distinction that the terminology implies, at least in the usual context in which it's used. So if you can share more about where you saw these terms, maybe it's possible that, what it meant was actually slightly different. So if you have any follow-up, then I'd be happy to look at it. Are we going to do lead code contests or not specifically, but hopefully the techniques that you learn in this course will help you solve lead code problems as well. We're not going to do them now, but yeah, I mean, like I said, next week we're going to have a more open-ended session, so maybe lead code can be one of the sources for problems that we take up next time.
Excuse me, ma'am.
Yeah.
Ma'am, I think it'd be great if we could just get the next assignment as soon as the deadline for the previous one ends.
Yeah, I think I'm sorry about this particular week. I think as I said, we will hopefully have an extended deadline for the week 8 assignment and the usual deadline for the week 9 assignment. And I think both of them, if they're not already up on the portal, they should be by tonight or latest tomorrow. Yeah.
Oh, okay. Thank you, ma'am.
So I hope that helps. Yeah, like I said, sorry for the delay this time, but thanks. Yeah. Now there's just one last comment about syllabus. I'm not sure in what context that question came up, but if you mean syllabus for the exam for this course, then that's just pretty much everything that's covered in these 12 weeks. So that would be ad hoc and 3D and DSU, all of these graph topics, starting from BFS, DFS traversals and shortest paths and minimum spanning trees and flows, and then finally dynamic programming. So that's essentially the syllabus for this course. So if you just stick to the topics and revise the assignments, you should be good. So yeah, hopefully that addresses that. And I think that was all the questions that came up on the stream. And if there are no other questions here, then I think we can kind of wrap this up. I'd just like to thank Nipun for the very nice explanation for the question that we had in week 7. Yeah. So this was fun. Thank you so much for joining, everybody who came in, and thanks for the nice discussion. We will see you all next week. So thanks, everybody. Bye for now and good night. So Mr. Karthik, we can probably stop the live stream as well. Yeah.